For a moment, imagine that everything around you becomes very quiet. The day has already settled into evening. The sounds of activity slowly soften. Perhaps there is a distant hum somewhere far away, or the gentle movement of air brushing against a window. Nothing urgent is happening. Nothing demands your attention. All that remains is the steady presence of time. You notice it first in small ways. Your breathing rises and falls, slow and steady. Your heart beats in a rhythm that has been with you since the moment you were born. One beat follows another, like footsteps along a path you cannot see. Time moves quietly through your body. You may not usually think about it, but every second that passes is felt somewhere within you. Your lungs expand, then relax. Your eyelids blink. Even the thoughts drifting through your mind appear and fade with their own gentle timing. Time, in this simple sense, feels familiar. It feels like the ticking of a clock on a wall. Like the steady turning of pages in a book. Like sunlight slowly crossing a room during the afternoon. Morning becomes afternoon. Afternoon becomes evening. Evening becomes night. And then, without effort, the cycle begins again. Because of this steady rhythm, it is easy to believe that time is something simple. Something constant. Something that flows the same way everywhere. But the universe has a habit of quietly surprising us. Long before scientists began studying the deep structure of reality, human beings sensed that time held a certain mystery. Ancient observers watched the stars moving slowly across the sky. They noticed seasons changing. They saw shadows lengthen and shorten across the ground. From these patterns, they built calendars and clocks. But the clocks we build are only tools. They measure time. They do not create it. And so a curious question slowly begins to appear. What exactly is time? It may seem like an obvious thing at first. Time feels like a river flowing steadily forward. The past drifts behind you, the future waits ahead, and the present moment is where you quietly stand. But if you pause and look more closely, that river becomes harder to describe. You cannot touch time. You cannot hold it in your hand. You cannot place it on a table and examine it from different angles. Yet everything you experience happens within it. Every memory you carry belongs to a moment that once existed. Every plan you imagine belongs to a moment that has not yet arrived. And somewhere between those two places, your life unfolds. For most of history, people believed time moved the same everywhere in the universe. Whether you were standing on Earth, drifting through space, or watching distant stars, time itself was assumed to tick at the same steady pace. 1 second here would be 1 second anywhere. It seemed perfectly reasonable. After all, clocks on Earth appeared to agree with one another. If two clocks were carefully built and placed side by side, they would tick together in quiet harmony. Tick, tick, tick. Each second following the last like the soft beat of a drum. But the deeper scientists looked into nature, the more subtle the universe began to appear. Because when you observe the world closely enough, you begin to notice something curious. Not everything experiences time in exactly the same way. At first, these differences are so small that they are almost impossible to detect. They hide beneath the surface of everyday life, like tiny ripples beneath a calm lake. But they are there. And once you notice them, the idea of time begins to change. Imagine for a moment that the universe is far larger and stranger than our daily experience suggests. Imagine that time is not a rigid line stretching from past to future, but something more flexible. Something that can stretch. Something that can bend. Something that can flow at different speeds depending on where you are. At first, this idea feels almost impossible. After all, your watch continues ticking the same way it always has. Your phone still measures seconds with perfect confidence. The sunrise tomorrow will arrive at its expected time. Everything seems normal. But the universe is vast. Beyond the quiet surface of everyday life lie immense stars, distant galaxies, and invisible forces shaping the structure of space itself. And within those enormous places, time behaves in ways that would seem strange from the comfort of Earth. There are regions of the cosmos where seconds stretch slightly longer. Places where time flows just a little more slowly than it does here. The difference might be tiny. Perhaps only a fraction of a second. But over long stretches of time, those small differences begin to matter. A clock placed in one location may slowly drift away from a clock placed somewhere else. Both are accurate. Both are correct. Yet they are not the same. This realization marks the beginning of a deeper journey into the nature of reality. Because if time itself can change depending on where you are, then time is not simply a background stage where events unfold. It is something woven into the universe itself. Something connected to the structure of space, the motion of objects, and the invisible forces shaping everything around us. The idea is quiet at first. Just a whisper of curiosity. But once you begin following that whisper, it leads you gently toward one of the most beautiful discoveries in science. Because time, it turns out, is not alone. It is closely connected to another familiar presence in your life. A force you feel every time your feet touch the ground. A force that holds oceans to the earth and guides the motion of planets around the sun. Gravity. And as the night deepens and your thoughts drift softly through the universe, you may begin to sense that this quiet force, the simple pull you feel every day, may also hold the secret to why time itself does not flow the same everywhere. Before you ever learned the word gravity, you were already feeling it. It was there the first time you stood up and felt your small feet pressed gently against the ground. It was there when you dropped a toy and watched it fall toward the floor. It was there every time you jumped, every time you walked, every time you lay down and felt the quiet weight of your body resting on a bed. Gravity has always been with you. It is so constant, so steady, that it rarely asks for your attention. Like the air around you or the beating of your heart, gravity simply continues its quiet work without announcement. You do not see it. You do not hear it. And yet its presence is everywhere. Imagine for a moment that gravity suddenly disappeared. The chair beneath you would no longer hold you in place. The oceans would lift from the surface of the earth. Buildings, trees, and mountains would drift slowly away into open space. Even the air itself would float upward and vanish into the darkness beyond the sky. But gravity does not disappear. It remains steady, patient, and reliable. Because of gravity, the earth holds you gently in its embrace. Because of gravity, the moon circles our planet in a slow and silent dance. Because of gravity, the planets travel around the sun, following graceful paths that repeat year after year. Gravity is the quiet architect of motion. For a long time, people believed gravity worked like an invisible rope. One object somehow pulled on another, even across great distances. The Earth pulled on the Moon. The Sun pulled on the Earth. Every object in the universe tugged gently on every other object. This idea worked beautifully for centuries. It explained falling apples, rising tides, and the paths of planets across the sky. The laws describing gravity were elegant and powerful, allowing scientists to predict celestial motion with remarkable accuracy. And yet, there remains something mysterious about it. How could objects pull on one another through empty space? What was the mechanism behind this invisible attraction? No one could quite say. The universe seemed to be filled with an unseen influence, something that reached across enormous distances without any visible connection. For many years, this mystery simply remained part of the natural world. Gravity worked. That was enough. But curiosity is a gentle force of its own. And slowly, over generations of observation and thought, scientists began to notice patterns that hinted at a deeper explanation. They saw how gravity shaped the paths of comets that wandered through the solar system. They measured the delicate movement of distant planets. They observed the graceful arcs traced by objects falling through the air. Everywhere they looked, gravity revealed itself as a universal presence. From the smallest pebble to the largest star, everything with mass participated in this quiet relationship. But gravity did not only guide motion, it also shaped structure. Without gravity, the universe would be a very different place. Gas drifting through space would never gather together to form stars. Stars would never ignite their brilliant nuclear fires. Galaxies would never emerge as vast spirals of light stretching across the darkness. Gravity is the patient sculptor of the cosmos. It gathers scattered particles and slowly draws them together, allowing matter to organize itself into the enormous structures we see through telescopes. In the early universe, long before planets existed, gravity began its work. Clouds of gas slowly collapsed inward. As they grew denser, their centers warmed. Eventually, pressure and heat became strong enough to ignite nuclear fusion. The first stars were born. Each of those stars shone because gravity held them together. Inside their blazing cores, atoms fused into heavier elements, creating the building blocks of planets, oceans, and life itself. So the same force that gently holds your feet to the earth also played a role in creating the atoms inside your body. Gravity connects the smallest experiences of daily life to the grand story of the cosmos. Yet something about gravity remained incomplete. Scientists could measure its strength. They could predict its effects. But they still did not fully understand what gravity actually was. The answer would arrive in a quiet and unexpected way. Instead of thinking of gravity as a force pulling objects together, a new idea slowly emerged. What if gravity was not a pull at all? What if gravity was something deeper, something built into the very structure of the universe? To imagine this possibility, it helps to picture space itself not as empty nothingness, but as something with shape and structure. Something that can stretch. Something that can curve. Something that can respond to the presence of matter. Imagine a vast, invisible landscape filling the universe. When massive objects like planets or stars exist within that landscape, they gently change its shape. The presence of mass creates subtle curves and valleys, and objects moving through that landscape simply follow those curves. From this perspective, gravity begins to look very different. The Earth does not pull the moon with invisible ropes. Instead, the Earth shapes the space around it, creating a curved path that the moon naturally follows. Planets orbit the sun because the sun bends the space around it. Even falling objects are simply following the curved pathways created by Earth's presence. This idea would eventually become one of the most important discoveries in physics. Gravity was not just a force acting within space. Gravity was a change in space itself. And once scientists began exploring this new way of thinking, something remarkable became clear. If space could bend, then time might bend too. The quiet pull you feel every day, the gentle weight pressing your feet to the ground, might be doing more than guiding motion. It might also be shaping the flow of time itself. And somewhere beyond the familiar pull of Earth's gravity, across the deep landscape of the cosmos, space and time may be woven together in ways far stranger than anyone once imagined. But to understand that deeper connection, you must first picture the universe in a completely new way. Not as empty space filled with objects, but as something more like a vast cosmic fabric, softly stretching beneath the weight of stars. Now imagine the universe in a different way. Not as a cold emptiness filled with scattered stars, but as something more delicate. Something subtle and flexible. Something that stretches endlessly in every direction, like a vast, silent fabric. This fabric is not made of threads or fibers you could touch. It has no color, no texture, and no visible shape. Yet it forms the stage on which every planet, every star, and every galaxy exists. Physicists sometimes describe it as space-time, the deep structure that combines space and time into a single, unified landscape. But before thinking about time, it helps to picture the shape of space itself. Imagine a wide, smooth sheet stretched gently across an enormous frame. At first, the sheet is perfectly flat. Nothing disturbs its surface. Now imagine placing a heavy ball in the middle of that sheet. Slowly, the fabric dips beneath the weight. A shallow valley forms around the object, curving downward in a soft bowl-like shape. The ball does not pull the fabric downward by magic. Its weight simply presses into the sheet, changing the shape of the surface around it. This simple picture offers a gentle way to understand gravity. In the universe, massive objects behave like that heavy ball resting on the sheet. Planets, stars, and galaxies sit within the structure of space, and their presence bends the space around them. Where there is more mass, the curve becomes deeper. Where there is less mass, the fabric remains flatter. Now imagine placing a smaller ball somewhere on that sheet. Instead of remaining still, it begins to roll along the curved surface created by the heavier object. From a distance, it might look as if the large ball is pulling the smaller one toward it. But the truth is slightly different. The smaller ball is simply following the curve of the surface beneath it. This is how gravity begins to appear in the modern understanding of the universe. Planets are not being pulled through empty space by invisible ropes. Instead, they are moving along the curved pathways created by massive objects within the structure of space itself. The sun bends the space around it, creating a deep valley in the cosmic fabric. The Earth moves along that valley in a wide circular path. The moon does the same thing around Earth, following a smaller curve created by our planet's mass. Everything in the universe is quietly navigating these invisible shapes. And the fabric extends far beyond our solar system. Stars bend the space around them. Entire galaxies curve the fabric on even larger scales. Clusters of galaxies create enormous valleys stretching across millions of light years. The universe becomes a landscape of gentle hills and valleys, shaped by the presence of matter. Objects move along these curves the way water flows through the contours of land. Nothing is pulling. Everything is following the shape of space. This idea may feel strange at first, but it brings a surprising sense of harmony to the universe. Instead of countless invisible forces reaching across emptiness, everything becomes part of a single, interconnected structure. Mass-shaped space. Space guides motion. The dance of planets, stars, and galaxies becomes the natural movement of objects flowing through this cosmic landscape. But the story does not end there. Because the fabric of the universe is not made of space alone. It is woven from space and time together. At first, this idea is difficult to imagine. Space feels easy to picture. You can imagine distance, direction, and movement. Time feels different. Time is the rhythm of change. The slow unfolding of events. The quiet passage from one moment to the next. Yet modern physics reveals that space and time are not separate things. They are deeply connected. Every location in space is also a location in time. Every movement through space is also a movement through time. Together they form a single structure, space-time. When massive objects bend space, they also influence the flow of time within that curved landscape. The same valley that guides the motion of planets also changes the rhythm of time passing nearby. Where space bends more deeply, time begins to behave differently. Clocks placed near massive objects tick slightly slower than clocks placed farther away. The difference is incredibly small near Earth, far too small for your senses to notice. But with precise instruments, scientists can measure it. Time itself stretches gently in the presence of gravity. You can imagine it like a river flowing across uneven land. In some places the water moves swiftly. In other places it slows, winding through deeper channels. Time flows everywhere in the universe, but its pace is not perfectly uniform. It responds to the shape of space around it. And since space bends under the influence of mass, time bends with it. This realization changes the way we think about reality. Time is not a universal clock ticking the same way for everyone everywhere. Instead, time becomes part of the landscape. Something that curves, stretches, and shifts depending on where you are within the cosmic fabric. Near massive planets, time slows slightly. Near enormous stars, it slows a little more. Near the most extreme objects in the universe, places where gravity becomes almost unimaginably strong, time may slow dramatically. The universe becomes a place where different regions experience time at slightly different speeds. Every planet, every star, every galaxy, each exists within its own subtle rhythm of time. And all of it is shaped by the invisible fabric of space-time. The idea may feel gentle and quiet, yet it carries profound meaning. Because it suggests that time is not separate from the universe. Time is woven directly into its structure. The moments of your life unfold within this vast fabric, influenced by the same cosmic laws that guide the motion of distant galaxies. Every heartbeat you experience happens within the curved landscape of space-time. Every breath moves through a universe that is quietly shaping the flow of time itself. And somewhere in the early years of the 20th century, a young physicist began to realize this connection with extraordinary clarity. His name was Albert Einstein. And the idea that space and time form a single fabric bending under the presence of mass would soon transform our understanding of the universe forever. At the beginning of the 20th century, the universe seemed well understood. For centuries, scientists had carefully studied motion, light, and gravity. The laws describing these phenomena worked beautifully. Planets moved exactly where predictions said they would. Objects fell toward the Earth with perfect reliability. Machines could be built using precise mathematical rules. The universe appeared orderly, predictable, and stable. And at the center of this understanding was a simple idea: time flowed the same everywhere. A second on Earth was a second on the Moon. A second on the Moon was a second beside a distant star. Time was considered universal, a steady ticking clock that guided the rhythm of reality. But sometimes the deepest changes begin with the quietest questions. In the city of Bern, Switzerland, a young physicist worked in a small patent office. His job was not glamorous. Day after day, he reviewed designs for machines and electrical devices, carefully examining whether each invention was truly new. His name was Albert Einstein. While others around him focused on practical inventions, Einstein's mind often wandered toward deeper mysteries. During quiet moments at his desk, he thought about the nature of light, motion, space, and time. He did not begin with large experiments. He began with imagination. Einstein loved what physicists call thought experiments, mental journeys where you imagine unusual situations and follow their consequences carefully. One of his favorite questions was simple but powerful. What would it be like to ride on a beam of light? Imagine, for a moment, that you could travel alongside a ray of light moving through space. Light travels incredibly fast, about 300,000 kilometers every second. That is fast enough to circle the Earth more than 7 times in a single second. If you could somehow keep pace with that beam, what would you see? Would the light appear frozen beside you? Would it stand still in space? Einstein realized that something strange would happen. According to the laws of physics known at the time, light must always move at the same speed. No matter how fast you travel, light continues racing forward at that incredible pace. That meant something surprising had to give. If the speed of light never changes, then our ideas about space and time must change instead. This realization was the seed of Einstein's special theory of relativity, published in 1905. Relativity introduced a remarkable idea: time does not pass at the same rate for everyone. The faster you move, the more time changes. If 2 people move at very different speeds, their clocks will not tick at exactly the same pace. One clock may run slightly slower than the other. The effect is tiny at everyday speeds, far too small to notice. But at speeds approaching the speed of light, the difference becomes dramatic. Time itself begins to stretch. This discovery alone would have been revolutionary. But Einstein was not finished. Over the next decade, he continued thinking deeply about gravity, the familiar force that keeps your feet on the ground and guides the motion of planets. At first, Gravity seemed unrelated to his new ideas about time and motion. But Einstein sensed a hidden connection. He began imagining another thought experiment. Picture yourself inside a small room, perhaps an elevator with no windows. If the elevator were resting on Earth, you would feel your feet pressed against the floor. Gravity would pull you gently downward. Now imagine that the elevator were floating far away in space, completely removed from any planet or star. Inside that elevator, you would feel weightless. You would drift slowly through the air. But suppose the elevator suddenly began accelerating upward. As it accelerated, you would feel yourself pressed against the floor again, almost exactly the way gravity presses you to the ground on Earth. To someone inside the elevator, it would feel the same. Acceleration and gravity would appear indistinguishable. This simple insight became known as the equivalence principle, one of the central ideas behind Einstein's new understanding of gravity. If acceleration and gravity feel the same, then gravity might not be a traditional force at all. Instead, it might be connected to motion and the structure of space itself. Einstein began exploring a bold possibility. What if massive objects like planets and stars actually change the shape of space and time? What if gravity is not something pulling objects together, but rather the result of curved space-time guiding motion? For years he worked through complex mathematics, searching for equations that could describe this idea precisely. The task was extraordinarily difficult. Yet in 1915, after nearly a decade of effort, Einstein completed what would become one of the most profound theories in science, the general theory of relativity. General relativity revealed a new picture of the universe. Space and time were not fixed backgrounds where events unfolded. Instead, they formed a dynamic fabric, something that could bend, stretch, and curve. Massive objects changed the shape of that fabric. Planets followed the curves created by stars. Light itself bent slightly when passing near massive objects. And most surprisingly of all, time flowed differently depending on the strength of gravity. Where gravity was stronger, time moved more slowly. Where gravity was weaker, time moved a little faster. This was no longer just imagination. Over the following decades, scientists performed experiments confirming Einstein's predictions with remarkable precision. Clocks placed near massive objects tick slightly slower. Light bends around stars. The universe behaves exactly the way Einstein's equations describe. The quiet ideas born in a patent office reshaped our understanding of reality. Space bends. Time stretches. Gravity emerges from the geometry of the universe itself. And this discovery leads to an even deeper realization. If gravity can bend time even slightly, then time does not flow the same everywhere. Near powerful gravitational fields, the rhythm of time itself begins to slow. And in the next part of our journey, you will begin to explore what it truly means for time to move more slowly under the influence of gravity. Now that you have begun to imagine the universe as a fabric, a vast landscape of space and time woven together, a new question begins to rise quietly in your mind. What happens to time when that fabric bends? If space curves around massive objects like planets and stars, then time, which is woven into that same fabric, must respond as well. And this is exactly what the universe reveals. Where gravity becomes stronger, time begins to move more slowly. At first, the idea feels almost impossible. After all, time seems perfectly steady in everyday life. Your watch ticks at its familiar pace. Your phone counts seconds with calm precision. Morning still becomes afternoon, and afternoon still becomes night. Nothing appears to change. But the universe often hides its most fascinating behaviors beneath layers of subtlety. The slowing of time near gravity is incredibly small in the places where we normally live. On Earth, the difference is far too tiny for your senses to notice. Yet with delicate instruments, clocks so precise they can measure fractions of a billionth of a second, scientists have discovered that the effect is real. Time truly does change its pace. To imagine how this works, picture a calm river flowing through a wide landscape. In shallow areas, the water moves freely and quickly. But when the river enters a deep valley, the flow becomes slower and heavier, winding through the deeper channel carved into the land. Time behaves in a similar way. In regions where gravity is weak, time flows freely. But in places where gravity becomes stronger, time begins to slow, like water moving through a deeper valley in the landscape of space-time. Earth itself creates a small valley in this cosmic fabric. The mass of our planet gently bends space and time around it. Because of this curvature, time on Earth's surface moves just a tiny bit slower than it does farther away in space. The difference is incredibly small. If you carried one clock high into space and left another clock on Earth, the clock in space would tick ever so slightly faster. After a full year, the difference between the two clocks might only be a tiny fraction of a second. Yet that difference exists. The clocks would not agree. And this tiny disagreement tells us something profound. Time is not universal. It does not flow at the same pace everywhere. Instead, the flow of time depends on the shape of space-time around you. Gravity quietly stretches time. Imagine now traveling deeper into the universe. Suppose you approach a massive planet, much larger than Earth. Its gravity would be stronger, bending the fabric of space-time more deeply. In that region, time would slow slightly more. Clocks resting near the surface of that giant planet would tick slower compared to clocks far away in open space. Now imagine moving even closer to an enormous star, a star many times the mass of our Sun. The curvature of space-time around that star would be deeper still. Time would slow even further. The clocks there would move more slowly compared to clocks located far from the star's gravity. Yet the people living near that star, if such a place were possible, would not feel anything unusual. Their own clocks would seem normal. Their hearts would beat at the same rhythm. Their days would pass as expected. Time would feel perfectly ordinary to them. It is only when two clocks from different gravitational environments are compared that the difference becomes visible. Each region of space carries its own subtle rhythm of time. And the deeper the gravitational valley, the slower that rhythm becomes. This effect becomes even more dramatic when we consider the most extreme objects in the universe. Black holes. A black hole forms when a massive star collapses under its own gravity, compressing enormous amounts of mass into an incredibly small region. The gravity near a black hole becomes almost unimaginably strong. The fabric of space-time bends sharply downward, forming one of the deepest valleys in the universe. Near the edge of this valley, a boundary known as the event horizon, time slows dramatically. From the perspective of a distant observer watching from far away, a clock near a black hole would appear to tick slower and slower. Seconds would stretch into minutes. Minutes would stretch into hours. Eventually, the clock would appear to almost stop. But something fascinating happens here. If you were the one standing near that black hole, your own experience of time would still feel normal. Your heart would beat. Your thoughts would move. Your clock would tick exactly as expected. The slowing of time only becomes visible when compared to clocks located far from the black hole's gravity. This reveals something beautiful about the nature of time. Time is not a single universal rhythm shared by everyone everywhere. Instead, the universe contains many overlapping flows of time, each shaped by gravity and motion. Every planet lives inside its own slightly different tempo. Every star carries its own pace of time. Even different parts of a galaxy experience subtle variations. And yet these differences rarely disrupt the harmony of the cosmos. Planets still orbit their stars. Stars still shine for millions or billions of years. Galaxies still spin slowly through the darkness of space. The universe quietly manages these variations with extraordinary precision. Even here on Earth, scientists must account for these subtle effects. Satellites orbiting high above the planet experience slightly weaker gravity than objects on the surface. Because of this, time for those satellites moves a little faster than time on Earth. If engineers ignored this difference, the navigation systems guiding airplanes, ships, and smartphones would slowly drift out of alignment. So every day, hidden deep within the calculations guiding global navigation systems, tiny adjustments are made. These adjustments correct for the gentle stretching of time caused by gravity. A quiet reminder that the universe is more flexible than it first appears. Time stretches. Time bends. Time flows at slightly different speeds depending on where you are in the cosmic landscape. And yet, for most of us, the rhythm of time still feels steady and comforting. Your breath rises and falls. Your heart continues its patient rhythm. Moments unfold into minutes, minutes into hours. But beneath this calm surface, the universe continues shaping the flow of time with silent precision. Now imagine something moving through the universe with extraordinary speed. Not a planet. Not a star. Not even a spacecraft. Instead, imagine a single beam of light. Light travels faster than anything else we know. In a single second, it can circle the Earth more than 7 times. In just 8 minutes, sunlight crosses the vast distance between the Sun and our planet. It moves with quiet determination, racing across space with unwavering speed. And yet, even something as swift and constant as light cannot completely escape the influence of gravity. To understand this, picture a beam of light leaving the surface of a massive star. At the moment it begins its journey, the light carries a certain amount of energy. That energy determines its color, whether it appears blue, green, yellow, or red. The color of light is not just something our eyes experience. It is a physical property connected to the light's wavelength, the tiny distance between the peaks of its invisible waves. Shorter wavelengths appear blue. Longer wavelengths appear red. Now imagine that this beam of light begins traveling outward, climbing away from the strong gravity of the star. In a sense, the light must work to escape. Just as a ball thrown upward must push against gravity as it rises, light moving away from a massive object must also climb through the curved fabric of space-time. And as it climbs, something subtle happens. the light loses a small amount of energy. But light cannot slow down, its speed remains constant. Instead, the light stretches slightly, increasing the length of its wavelength. Its color shifts gently toward the red end of the spectrum. This effect is known as gravitational redshift. It is one of the quiet signatures of gravity's influence on light. The change is extremely small, far too subtle for human eyes to notice. But with sensitive instruments, scientists can measure it with remarkable precision. When light escapes from the surface of a massive star, its wavelength stretches ever so slightly. The deeper the gravitational field, the stronger this stretching becomes. And so the color of light carries hidden information about the environment it traveled through. It is almost as if the light whispers a story about the gravity it has encountered. This idea might seem abstract at first, but it offers powerful evidence for the connection between gravity and time. Because when light loses energy climbing out of gravity, it reveals something deeper about the nature of time itself. In the curved fabric of space-time, gravity affects not only motion but also the rhythm of physical processes. Atoms vibrate differently. Clocks tick at different rates. And light waves stretch as they move through regions where time flows differently. You can imagine light as a messenger traveling across the cosmic landscape. Every journey it makes carries subtle clues about the structure of the universe. Astronomers study these clues carefully. By observing how light changes as it travels through space, they can learn about distant stars, massive galaxies, and powerful gravitational fields that would otherwise remain invisible. For example, when scientists observe light escaping from the surface of a dense star known as a white dwarf, they notice that its wavelength is slightly stretched. This stretching matches the predictions of Einstein's theory of general relativity. The stronger the gravity, the more pronounced the redshift becomes. Even here on Earth, tiny versions of this effect can be measured. In carefully designed experiments, physicists send beams of light upward through tall towers or laboratories. As the light climbs away from Earth's gravity, its wavelength changes by an incredibly small amount. The difference is almost unimaginably tiny. Yet it is real. And it confirms once again that gravity shapes the flow of time and energy in the universe. But light does something even more remarkable. Not only does gravity stretch its wavelength, it can also bend the path that light travels. Imagine shining a beam of light past a massive star. Instead of moving in a perfectly straight line, the light curves slightly as it passes through the star's gravitational field. This bending happens because space itself is curved around massive objects. Light simply follows the shape of that curved space. The effect is small, but it becomes dramatic near extremely massive bodies. Entire galaxies can bend light from even more distant galaxies behind them, creating beautiful arcs and rings in the sky. Astronomers call this phenomenon gravitational lensing. The gravity of a massive object acts like a cosmic lens, bending and focusing light traveling across the universe. These natural lenses allow scientists to observe distant galaxies that might otherwise remain hidden. Light, once again, becomes the storyteller of the cosmos. Through its shifting color and bending path, it reveals the invisible architecture of space-time. And the deeper scientists look, the clearer the message becomes. Gravity does not merely pull objects together. It reshapes the environment through which everything moves, including light itself. This reshaping affects motion, energy, and time all at once. The universe behaves like a vast interconnected system where space, time, matter, and light all respond to one another. Even the fastest traveler in existence cannot ignore the gentle influence of gravity. Light may move swiftly across the cosmos, but its journey is still guided by the quiet curves of space-time. And as you continue exploring this idea, another question begins to emerge. If gravity can stretch light and slow the flow of time, what happens to clocks placed in different parts of the solar system? What would happen if one clock rested quietly on Earth, while another orbited near the Sun, or drifted beside the giant planet Jupiter? The answers reveal something beautiful about the many rhythms of time that exist throughout the universe. Imagine, for a moment, that you possess a collection of perfect clocks. Not ordinary clocks like the ones on your wall or the ones inside your phone, but incredibly precise instruments, clocks so accurate that they would lose only a single second over millions of years. Now imagine placing these clocks in different places across the solar system. One clock remains here on Earth, resting quietly on the surface of the planet. Another travels far away, drifting gently through the open darkness of space. A third moves closer to the Sun, orbiting deep within the strong pull of solar gravity. Each clock begins ticking at the same moment. Tick, tick, tick. At first, everything seems identical. The clocks move in perfect agreement, each second following the last with steady rhythm. But the universe is never quite as simple as it first appears. Because each of these clocks lives within a slightly different gravitational environment. Earth itself creates a gentle valley in the fabric of space-time. Its gravity bends the cosmic landscape just enough to influence the passage of time. But farther away from Earth, gravity becomes weaker. Closer to the Sun, gravity becomes stronger. And according to Einstein's understanding of gravity, these differences in gravitational strength subtly change the flow of time. The clock drifting far out in space, far from any massive object, experiences weaker gravity. In that quieter region of space-time, time flows just a little faster. Meanwhile, the clock orbiting closer to the Sun experiences stronger gravity. The deeper curvature of space-time slows the passage of time slightly. Each clock continues ticking faithfully according to the physics of its surroundings. Yet when the clocks are later compared, they will not agree. The differences are extremely small, far too tiny to notice with human senses. But they are measurable with modern instruments. The clock near the Sun will have ticked slightly fewer seconds. The clock far out in space will have ticked slightly more. This gentle disagreement between clocks reveals something profound about the structure of the universe. Time is not perfectly uniform. Instead, it flows differently depending on where you are in the cosmic landscape. Every planet, every star, every galaxy shapes the rhythm of time around it. You can imagine the universe as a vast orchestra, with each region playing its own subtle tempo. Earth has its rhythm. The Moon has another. Jupiter, with its enormous mass, bends space-time more deeply than Earth does, creating an even slower flow of time near its surface. The Sun bends the fabric of space-time even more dramatically. Closer to the Sun, time slows slightly more compared to distant regions of space. And yet, from within each location, nothing seems unusual. If you stood on the surface of Jupiter, assuming you could survive its crushing atmosphere, your heartbeat would feel normal. Your clock would tick normally. The rhythm of daily life would unfold exactly as expected. Time always feels normal from the inside. It is only when clocks from different gravitational environments are compared that their differences become visible. This idea might seem abstract, but it plays a surprisingly practical role in modern life. High above Earth, a network of satellites circles the planet every day. These satellites belong to the Global Positioning System, or GPS, a navigation system that helps guide airplanes, ships, cars, and even the maps inside your smartphone. Each satellite carries extremely precise atomic clocks. These clocks must stay synchronized with clocks on Earth in order for the system to calculate accurate positions. But the satellites orbit far above the planet's surface, where gravity is slightly weaker. Because of this, time for the satellites moves a little faster than time for clocks on Earth. If scientists ignored this effect, the GPS system would slowly accumulate errors. Navigation signals would drift farther and farther from their correct locations. Within a single day, positions could become wrong by several kilometers. To prevent this, engineers carefully adjust the satellite clocks to account for the difference in gravitational time flow. Every day, tiny corrections are made, corrections based directly on Einstein's theory of relativity. The stretching and bending of time is not just an abstract idea. It quietly shapes the technology guiding millions of people around the world. Yet the solar system offers even more fascinating examples. Consider the planet Mercury. Mercury orbits very close to the Sun, deep within the Sun's powerful gravitational field. Because of this, time on Mercury flows slightly slower compared to time on Earth. The difference is extremely small, but measurable. Similarly, near massive stars or dense stellar remnants like neutron stars, the effect becomes stronger. The closer an object moves toward powerful gravity, the slower time flows relative to distant regions of space. And so the universe reveals an elegant pattern. Gravity shapes space. Curved space guides motion. And curved spacetime influences the rhythm of time itself. Every planet and star becomes a small island of altered time within the larger sea of the cosmos. Most of these variations are gentle, subtle, and quiet. But there are places in the universe where gravity becomes far more intense. Places where the bending of spacetime becomes dramatic. Places where time slows so strongly that the difference becomes impossible to ignore. These are the regions surrounding one of the most mysterious objects known to science: black holes. Near these extraordinary objects, the curves in spacetime become so deep that time itself begins to behave in ways that challenge our deepest intuitions. And as you continue drifting through this quiet exploration of the universe, your journey now moves toward the edge of one of those immense gravitational valleys, a place where the slowing of time becomes almost unimaginable. Far beyond the familiar paths of the planets, deeper than the quiet glow of distant stars, there exist places where gravity gathers with extraordinary strength. These places are known as black holes. To imagine how they form, begin with a massive star far larger than our Sun. For millions of years, the star burns brightly, balancing two powerful forces. Inside its core, nuclear fusion releases enormous energy. That energy pushes outward, resisting the star's own gravity, which is constantly trying to pull everything inward. For a long time, these forces remain in balance. But eventually the fuel inside the star begins to run out. The outward pressure weakens. Gravity, patient and relentless, begins to take control. The star collapses inward under its own weight. For smaller stars, this collapse eventually stabilizes, forming dense objects like white dwarfs or neutron stars. But for the most massive stars, the collapse continues far beyond those limits. The star compresses into an incredibly small region. Gravity becomes so strong that the fabric of space-time curves steeply downward, forming one of the deepest valleys in the universe. A black hole is born. At the center of this region lies what physicists call a singularity, a point where matter has been compressed to extraordinary density, and where our current understanding of physics begins to struggle. But long before reaching that mysterious center, something remarkable happens. Surrounding every black hole is an invisible boundary called the event horizon. The event horizon is not a physical surface like the ground beneath your feet. It is a boundary in space-time, a point beyond which nothing can escape. Not even light. Once something crosses this boundary, the gravitational pull becomes so strong that all paths lead inward. Escape becomes impossible. But what makes black holes especially fascinating is not just their ability to trap matter and light. It is what they do to time. Imagine observing a clock slowly drifting toward a black hole from a safe distance far away. As the clock approaches the black hole's gravity, something unusual begins to happen. From your distant viewpoint, the clock appears to tick more slowly. Seconds stretch. Minutes lengthen. The closer the clock moves toward the event horizon, the slower it seems to run. Eventually, from your perspective, the clock appears almost frozen in time. Its ticking slows to an unimaginable crawl. Just before reaching the event horizon, it appears nearly stopped. This effect is known as gravitational time dilation, and near black holes it becomes extremely dramatic. But something curious must be remembered. This slowing of time is what you observe from far away. If you were the one traveling with that clock toward the black hole, your experience would feel completely normal. Your heartbeat would remain steady. Your thoughts would flow at their usual pace. Your clock would tick exactly as it always has. From your perspective, nothing unusual would seem to happen at all. This contrast reveals something extraordinary about time in Einstein's universe. Time is not absolute. Different observers can experience time differently depending on their position within the curved structure of space-time. Near a black hole, those differences become enormous. To someone watching from far away, events near the event horizon unfold more and more slowly. Light escaping from that region becomes stretched and dim, shifting toward deeper and deeper shades of red. Eventually, the light fades beyond visibility. To the distant observer, the falling object appears to freeze at the edge of the event horizon, slowly fading away. Yet for the traveler moving toward the black hole, the journey continues smoothly forward. Space and time guide their path inward without interruption. These two perspectives, the distant observer and the falling traveler, are both valid within the strange geometry of space-time. And this reveals one of the deepest insights of modern physics. The flow of time is not the same everywhere. Gravity reshapes the rhythm of time itself. Black holes simply reveal this truth in its most extreme form. Yet black holes are not merely cosmic traps. They also play important roles in the structure of the universe. At the centers of many galaxies, including our own Milky Way, enormous black holes quietly reside. These supermassive black holes contain millions or even billions of times the mass of our Sun. They influence the motion of stars throughout their galaxies. They shape the growth and evolution of cosmic structures. In some cases, matter falling toward these black holes forms swirling disks of glowing gas that shine brighter than entire galaxies. Even though black holes themselves remain dark, the environment around them can become some of the most energetic regions in the universe. And yet, beneath all that activity lies the same quiet principle you have been exploring throughout this journey. Mass bends space-time. Curved spacetime shapes motion, and curved spacetime alters the flow of time itself. Near ordinary planets, the effect is gentle. Near stars, it becomes stronger. Near black holes, it becomes profound. Time stretches so dramatically that the difference between distant observers and nearby travelers grows enormous. The universe becomes a place where time itself depends on location. Yet gravity is not the only influence shaping the rhythm of time. There is another factor, something equally fundamental to the nature of reality. Motion. The speed at which you move through space can also change the flow of time. And when motion and gravity work together, they reveal an even deeper picture of how the universe guides the passage of moments. So far in your quiet journey through the universe, you have discovered something remarkable. Gravity can stretch time. Where gravity grows stronger, time flows a little more slowly. Where gravity becomes weaker, time moves a little faster. Every planet, star, and galaxy gently reshapes the rhythm of time around it. But gravity is not the only influence that can change the flow of time. Motion plays a role as well. To begin exploring this idea, imagine something very simple. Picture yourself standing still on a calm evening, watching the world around you. Perhaps you are outside, feeling the quiet presence of the night sky. The stars appear fixed above you, and time seems to pass in its usual steady rhythm. Now imagine that you begin moving faster and faster. First you walk. Then you run. Then you travel in a car, speeding along a road. Next you imagine boarding an airplane, crossing the sky at hundreds of kilometers per hour. At these everyday speeds, nothing about time seems to change. Your watch continues ticking normally. Your heartbeat keeps its steady rhythm. Minutes still unfold into hours just as they always have. But as your speed increases further, something subtle begins to happen. At first the effect is far too small to notice. Yet according to the laws of physics discovered by Albert Einstein, time for a moving object passes slightly more slowly compared to time for an object at rest. This phenomenon is known as time dilation. It means that the faster you move through space, the more time stretches along your path. The difference is extremely small at the speeds humans normally experience. Even a jet airplane traveling across the sky produces only a tiny change, a difference measurable only with incredibly precise atomic clocks. But scientists have performed careful experiments to confirm this effect. Clocks carried aboard fast-moving airplanes have been compared with clocks left on the ground. When the clocks are brought together again, they show slight differences. The clocks that traveled quickly have experienced slightly less time. Their seconds were stretched just a little. This may sound strange, but it becomes easier to understand if you think of space and time as deeply connected. In the universe described by Einstein's theory of relativity, space and time form a unified structure known as space-time. Every object moving through the universe travels through both space and time at the same time. But there is a balance between these two kinds of motion. The faster something moves through space, the less quickly it moves through time. It is almost as if the universe distributes motion between the two. When more motion occurs in space, less motion occurs in time. This is why clocks moving at high speeds tick slightly slower. Their journey through space changes the way they move through time. At ordinary speeds the effect is tiny. But near the speed of light, the difference becomes dramatic. If a spacecraft could travel extremely close to the speed of light, time inside the spacecraft would slow dramatically compared to time on Earth. Astronauts traveling on such a journey might experience only a few years passing, while decades or even centuries passed for people back home. This idea has often appeared in stories and films about space travel. Yet it is not science fiction. It is a real prediction of Einstein's theory, confirmed by experiments with high-speed particles in laboratories. When particles known as muons are accelerated to speeds close to the speed of light, they live far longer than they normally would. From their own perspective, their internal clocks run normally. But from our perspective, their time has stretched. Their motion through space has slowed their motion through time. Now something even more beautiful begins to appear. Gravity and motion both influence the flow of time. Near massive objects, gravity slows time. At high speeds, motion slows time as well. In many situations throughout the universe, both effects occur together. Consider astronauts orbiting the Earth aboard a spacecraft. Their motion through space tends to slow their clocks. But their distance from Earth places them in slightly weaker gravity, which causes their clocks to run slightly faster. The two effects partially balance one another. Engineers studying satellite systems must carefully calculate both influences in order to maintain accurate timekeeping. Once again, the flexible nature of time becomes part of everyday technology. But beyond the practical applications lies a deeper insight. Time is not a fixed background where events simply occur. Time is part of the structure of the universe itself. It bends under gravity. It stretches with motion. Every path through space carries its own flow of time. Two travelers following different routes through the cosmos may experience different amounts of time passing. Their journeys shape their personal rhythms of time. And yet, despite all these variations, the universe remains beautifully consistent. The laws of physics continue working in every frame of reference. Stars burn. Planets orbit. Light travels across unimaginable distances. Each process unfolds according to the flow of time within its local environment. The universe becomes a vast tapestry of motion and gravity, woven together through space-time. And within this tapestry, time flows like a river branching into countless gentle streams. Some streams move slightly faster. Others move slightly slower. But all remain connected within the same cosmic landscape. The deeper scientists explore this landscape, the more they realize that measuring time precisely becomes one of the most important tools in understanding the universe. Because by observing tiny differences in time, differences measured in fractions of a billionth of a second, scientists can reveal the hidden structure of space-time itself. And so the next step in your quiet journey leads toward the instruments that allow humans to measure time with extraordinary precision. Clocks so accurate that they can detect the gentle stretching of time caused by gravity and motion throughout the universe. Time, invisible yet ever-present, seems to tick steadily as we move through our daily lives. Our hearts beat. Our thoughts drift. The sun rises and sets. Minutes and hours flow in comforting regularity. But as you have discovered on this journey, time is more flexible than it first appears. Gravity bends it. Motion stretches it. And now, you begin to see how humans have learned to measure its subtle variations with extraordinary care. Imagine a clock, not an ordinary one, but a clock so precise that it measures time with incredible accuracy. This is an atomic clock, a remarkable instrument that counts the vibrations of atoms as they oscillate. Most atomic clocks use cesium or rubidium atoms. Inside these clocks, atoms absorb and emit light at extremely consistent frequencies. Each vibration acts like a heartbeat of time, allowing the clock to measure seconds with unimaginable precision. These clocks can remain accurate to within a billionth of a second. That means over thousands of years, the clock would lose only a few seconds. Such precision may seem unnecessary at first glance. But when studying the flow of time across the universe, this level of detail becomes essential. Consider the satellites that orbit high above Earth, part of the Global Positioning System, GPS. Each satellite carries an atomic clock aboard, tracking time with unwavering precision. You might not think about it as you follow directions on your phone, but these clocks are essential to finding your way. Even a tiny discrepancy in time could cause your position to appear kilometers away from reality. The satellites orbit at altitudes where gravity is slightly weaker than on the surface of Earth. As a result, their clocks experience time slightly faster than clocks on Earth. At the same time, these satellites move at high speeds around the planet. According to Einstein's theory, motion causes time to slow slightly. The combined effect of weaker gravity and faster motion must be calculated carefully to ensure accuracy. Without these adjustments, the system would drift. Distances would be miscalculated. And the quiet reliability of modern navigation would falter. Atomic clocks allow scientists and engineers to account for both the stretching of time caused by gravity and the slowing of time caused by motion. Scientists also perform experiments on Earth to detect time's subtle variations. Imagine two atomic clocks, one placed at the base of a tall tower and another at its top. Gravity is slightly weaker at the higher elevation. The clock at the top ticks ever so slightly faster. Over days, months, or years, the difference becomes measurable. Even the smallest variations in height or gravitational strength reveal that time is not uniform. Beyond Earth, these measurements expand our understanding of the solar system and beyond. By tracking the signals of spacecraft traveling near planets or stars, scientists can measure the slight slowing of time caused by stronger gravity. Light beams sent between these craft act as messengers, carrying tiny clues about the rhythm of space-time itself. The practical applications of these discoveries are everywhere. Satellites provide accurate weather predictions. They guide airplanes and ships. They synchronize communication systems across continents. All of this depends on our ability to measure the flow of time with exquisite precision. But even as scientists develop instruments capable of detecting time's gentle fluctuations, the universe continues to surprise. Observations of distant stars, pulsars, and black holes reveal environments where gravity bends time in ways far more dramatic than anything experienced on Earth. A clock near the surface of a neutron star, for example, would tick incredibly slowly compared to one far away in interstellar space. These observations do more than satisfy curiosity. They test the limits of our understanding, confirming the predictions of Einstein's theories with ever greater accuracy. Each measurement provides a window into the hidden structure of the cosmos, revealing how space and time weave together in an elegant, dynamic tapestry. Yet even as instruments measure these effects, the experience of time remains deeply personal. Your heartbeat, your breathing, the passage of moments in your life, all of these continue to unfold according to the rhythm of your immediate environment. The universe's grand variations in time coexist with your own quiet, familiar flow of life. And there is a profound comfort in this. You are part of a universe that is vast, dynamic, and precise. Gravity shapes the paths of planets and the flow of seconds. Motion stretches and bends the rhythm of time. But even within these complexities, a sense of harmony exists. Everything operates according to laws that are consistent and predictable, allowing life, thought, and motion to continue. As you drift through this reflection, consider the subtle beauty of these measurements. Each atomic vibration, each adjustment to a satellite's clock, each observation of light stretched across space, is a testament to human curiosity and patience. Through careful observation, you can perceive the universe not just as a place where events occur, but as a living, breathing structure where time itself is flexible and responsive. Even here on Earth, in the quiet of your own room, the effects of gravity and motion subtly influence time. You may not notice, but every footstep, every rise and fall in altitude, even the gentle movements of satellites overhead, contribute to the complex symphony of time around you. Atomic clocks allow humans to detect and measure these variations, turning abstract cosmic principles into practical tools that guide daily life. And yet, as precise as these instruments are, they only hint at the deeper mysteries still to be explored. The most extreme environments, the edges of black holes, the far reaches of galaxies, the heart of neutron stars, still hold secrets. Time behaves in ways that are both measurable and profoundly mysterious, stretching the imagination as much as it stretches seconds. As you contemplate these quiet measurements, you begin to sense a larger truth: the universe is not rigid. Time is not absolute. Gravity bends it. Motion stretches it. And through the careful work of scientists, you can observe, measure, and even anticipate the subtle variations of time throughout space. By now, you have traveled far across the cosmos in thought and imagination. You have seen planets and stars shaping time, light bending and stretching, clocks moving at different rhythms depending on their location and speed. You have glimpsed black holes, where time almost stops, and satellites whose precise clocks quietly confirm Einstein's predictions. All these glimpses reveal a central truth: the universe is not a rigid, mechanical place. It is flexible, dynamic, alive in its own gentle rhythms. Now, imagine returning home, slowly bringing yourself back to Earth, yet carrying the knowledge of these cosmic flows. Step outside and feel the ground beneath your feet. Your body rests inside a valley of gravity, where time moves just a little more slowly than it does far above in orbit. Every heartbeat, every inhale, every moment passes at a pace shaped by the planet you call home. Even without noticing, you are living inside a flexible universe. Consider the moon overhead. Its pull affects the tides, and subtly, the flow of time in its own small gravitational field. Though the effect is tiny, it is real. The same applies to every object with mass: Jupiter, the Sun, distant stars, galaxies far away. Each shapes the rhythm of the space-time surrounding it, and in turn, every moment you experience is intertwined with these cosmic influences. Time, once thought to be universal and unchanging, is now revealed as a personal, flowing landscape. You live within valleys and gentle slopes of time, shaped by mass, motion, and the curvature of space itself. Your journey through life, your steps, your thoughts, your awareness all occur amid these invisible currents. In this sense, you are not separate from the universe. You are a participant in its rhythm, a traveler along its undulating temporal fabric. The universe no longer feels like a rigid clockwork mechanism with unchanging gears. Instead, it resembles a vast, soft tapestry. Each thread represents space, each weave carries the flow of time, and every movement, every pulse, is interconnected. Massive objects pull and bend the threads. Light threads its way along curves. Motion tugs gently on the flow of time, adjusting it ever so slightly. Your life unfolds within this intricate weave. Imagine yourself lying in a quiet meadow at night, the stars stretching endlessly overhead. You are aware of the steady passage of your own breathing, the soft rhythm of your heartbeat. Above you, planets orbit, stars burn, light travels across millions of kilometers, all guided by the subtle rules of space-time. Each of these movements has its own rhythm, yet they all harmonize. And you, right here, experience the intersection of these rhythms within your own perception of time. Even the technology you rely on connects you to this cosmic flow. GPS satellites orbit overhead, adjusting their clocks for gravity and motion. Communications signals move through space, guided by the curvature of the universe. Atomic clocks tick quietly in laboratories, measuring fractions of seconds to reveal the bending and stretching of time. Every day, unseen, humanity interacts with the flexible fabric of the cosmos, making use of its subtle rules to navigate and communicate across the planet. And yet, the universe is not fully known. While you have glimpsed the principles, there are still mysteries. The interiors of black holes remain hidden. The deepest reaches of interstellar space stretch beyond our ability to explore. And even here on Earth, every particle, every photon, is subtly influenced by the surrounding mass and motion. Your awareness of this flexibility offers a gentle, meditative perspective. You live in a place that is alive, responsive, and intertwined with all things. You might take a slow breath now, feeling the connection. Gravity pulls you toward the Earth, shaping the pace of your time. The Sun's immense gravity pulls on the planets, shaping their orbits and the flow of time around them. Distant stars, galaxies, and even light crossing the cosmos, all exist within the same interconnected framework. The universe is alive not in a conscious sense, but in the way space, time, and matter respond to one another, flowing and bending, stretching and curving. Your body, your mind, your thoughts all exist within these gentle rhythms. You are neither entirely separate from the universe, nor entirely dictated by it. You are part of its ongoing story, moving with it, participating in its dance. Every heartbeat is synchronized, however subtly, with the pulses of distant stars, the curvature of space, and the flow of time around massive objects. This awareness invites calm and reflection. It grounds you in the present while connecting you to the vast cosmos. And as you rest in this understanding, consider the poetic beauty of it. Each step you take, each moment you experience, is guided by invisible rhythms. The universe is vast, yet you are intimately connected to it. You are small, yet every action is part of a larger dance. Gravity, motion, and time all continue their work, imperceptible yet undeniable. The universe is patient, flexible, and enduring. And so are you, living within its gentle currents. Even as the night deepens, you feel this quiet connection. You are a participant in a living cosmos. Each breath, each moment, is part of the flexible flow of time and space. Planets orbit. Stars shine. Light stretches and bends. And your awareness, your consciousness, moves along with them. You are part of this continuous, graceful unfolding. As you allow yourself to rest in this knowledge, your mind naturally drifts toward curiosity. If time bends here, how do scientists track its variations across the universe? How do we translate the flexible flow of cosmic time into measurements we can use on Earth, guiding satellites and understanding distant stars? The next step of your journey begins to lead you quietly into the precise instruments that reveal the universe's hidden rhythms. Now, as you lie quietly in the soft embrace of night, consider the vast expanse that stretches beyond your senses. You have journeyed across planets, drifted near stars, followed beams of light, and peered into the depths of black holes. You have discovered that gravity curves space, motion stretches time, and atomic clocks reveal the subtle rhythms that govern the universe. Yet even after all this, a quiet mystery remains. Even with all the experiments, observations, and calculations, the universe still holds secrets. The most extreme corners of space, the deep interiors of black holes, and the nature of time itself continue to challenge the human mind. Science has illuminated much, but every answer seems to open the door to further questions. And there is beauty in this. The universe is patient, unhurried, waiting for you and for humanity to uncover its truths at the right pace. Imagine a black hole again, its gravity so strong that time nearly stops. Even as scientists observe its effects from a distance, its interior remains hidden from view. How does time behave at the singularity? What laws govern matter compressed beyond comprehension? The questions linger, unanswered, as the cosmos quietly persists. This is a reminder that understanding is a journey, not a destination. The universe does not hurry, and neither must you. You might feel a gentle sense of awe, sensing that you are part of this ongoing exploration. Every breath you take, every heartbeat, occurs within a cosmic environment shaped by the bending of space and the stretching of time. The rhythms of your life are woven into the same fabric that guides planets, stars, and galaxies. There is a quiet harmony in this realization. The universe is immense, yet you exist within it, participating in its ongoing story. Even the laws of physics, as elegant as they are, leave room for wonder. Gravity shapes time, yet the quantum world, the tiny, invisible building blocks of matter, behaves differently, sometimes unpredictably. Scientists search for ways to unite the behavior of the very small with the behavior of the very large. The quest to reconcile quantum mechanics and general relativity continues, a gentle reminder that the universe is full of subtle, layered mysteries. Your mind might drift to light again, moving across the cosmos, carrying messages of curved spacetime, redshifted by gravity, bending around galaxies, whispering secrets across millions of kilometers. Light travels patiently, revealing what you cannot directly see, bridging distances and ages. Even the faintest photon is a storyteller, hinting at phenomena that remain beyond direct observation. The universe communicates softly, if only you are attentive enough to listen. The instruments humans have created, atomic clocks, satellites, telescopes, allow glimpses into these mysteries. Yet every discovery sparks new curiosity. The more precise our measurements become, the more we realize how nuanced and intricate the universe truly is. Gravity bends time subtly across planets, motion stretches it slightly, black holes warp it profoundly, yet all these variations exist within a larger, coherent cosmos. Science provides tools to understand, but never exhausts the wonder of what is out there. And here, in the quiet of your mind, you begin to feel the rhythm of your own time. Your breath, your heartbeat, your thoughts, all of them move forward within the same flexible framework that governs planets and stars. You are part of a universe that is both structured and mysterious, predictable in its patterns yet infinite in its possibilities. Each moment you experience carries the subtle influence of gravity, motion, and cosmic flow. You might imagine the vast web of galaxies, each containing billions of stars, each star bending time slightly, each planet following its own rhythm. And all of this stretches across space and time, carrying light, energy, and motion across unimaginable distances. The universe is alive in its structure, patient in its unfolding, and generous in its capacity for wonder. And you, quietly aware, are a part of it, moving along the same flowing currents that govern everything else. As you rest in this awareness, a gentle realization settles over you, even after centuries of study, even after the most precise measurements, the universe retains its quiet mysteries. Time bends. Space curves. Gravity influences everything. Motion stretches seconds. Light carries messages across the cosmos. And yet, there remain corners unseen, questions unanswered, secrets patiently waiting to be discovered. This patience is comforting. The universe does not demand immediate understanding. It exists in its own rhythm, allowing you to rest, explore, and wonder at your own pace. Perhaps now, as you feel the rhythm of your own body, you sense a harmony with the universe. The laws of physics, the bending of space-time, the stretching and slowing of moments, all of it surrounds and passes through you. You are both observer and participant, quietly immersed in the flow of cosmic time. The universe continues its work silently, patiently, beautifully. It does not hurry, and you too can move through your life with the same calm awareness, attuned to the subtle rhythms of the world around you. And as you drift further towards sleep, your mind opens gently to a final reflection. The universe is both known and unknown, precise and mysterious, vast and intimate. Time flows differently depending on where you are and how you move. Gravity molds the cosmos. Motion stretches its moments. Light carries whispered stories of space-time. And you, lying here quietly, are a part of this extraordinary, flowing, flexible universe. You rest within its rhythms, connected to its secrets, and gently carried toward the next moment, the next discovery, and the quiet continuation of all that is. The mysteries of gravity and time remain, patient and enduring, waiting for tomorrow's explorers and for your own mind to wander quietly in wonder tonight.